Hello guys, today I would like to deliver the last chapter for this semester, that is chapter 14 about thermodynamics. So the photo on this slide is an application of the thermodynamic concept, which is like the jet engine of the aeroplane, the freezer, and also the air conditioner. But in my explanation, I will going to focus on the remember and understand level only. So firstly, we want to see what is meant by thermodynamic. So the thermodynamic actually is a study of relationship involving heat, mechanical works, and other aspects of energy and energy transfer for the system. In other words, it involves energy, so that it will obey the conservation of energy. And of course, when we study about thermodynamic, we must also study about the system of thermodynamic. For example, like the jet engine and the chiller of the central air conditioner are example for thermodynamic system. So the other example of thermodynamic system, such as popcorn, is also thermodynamic system. Our body also thermodynamic system. So actually, what is thermodynamic system? Thermodynamic system is any collection of objects that is convenient to regard as unit, may have the potential energy to exchange energy with its surrounding. So for example, when energy loss, it will be to the surrounding, and maybe the energy can also come into the system, that is maybe chiller, maybe jet engine, and other example of thermodynamic system. So now we are going to look at on the overview for this topic. So in this topic, we are going to learn about first law of thermodynamics. And after that, there are 4 thermodynamic processes. And after that, in that thermodynamic processes, we're going to look at on the pressure volume graph and work done. Actually, we have another law called second law of thermodynamics, but that not been discussed in this curriculum or matriculation level. You're going to learn that if you go to the higher level, that is university level, and you take thermodynamics course. So now we are going to look at on the first subchapter or subtopic, which is first law of thermodynamics. What is the outcome for the level C1, that is state first law of thermodynamics? So if you can see on this slide, there is one equation that is Q equal to delta U plus W. This is the equation for the first law of thermodynamics. So the Q actually is heat, and U is internal energy of the gas. So delta U is change in the internal energy of the gas, and W is work done. The statement of the first law of thermodynamics is heat supply to a system, which is a gas, is equal to the sum of increase in internal energy of the system and the work done by the system. Or mathematically, so it's more easier, can be written as Q equal to delta U plus W, where the Q is amount of heat, delta U is the change in the internal energy of the system, which is a gas, and W is work done by the system, the gas. And this, you can calculate the delta U by using the final internal energy minus with the initial internal energy. And this internal energy we refer to internal energy formula of the gas, that is U equal to F over 2 nRT. So this topic have a close relation with the previous topic, that is kinetic theory of gases. So since the unit of Q is joule, therefore the unit of delta U and W also joule. Actually, the first law of thermodynamics generalization of the principle of conservation of energy. In other words, this first law of thermodynamics obey the conservation of energy. So it means that the total energy always conserved. If the Q, the input Q is 10 joule, so the delta U plus W also must be 10 joule. So there is no energy loss from the system. The energy loss means here, if the Q is 10 joule, so the delta U plus W also must be 10 joule, cannot be less than that. And then the change in the internal energy or delta U independent of path. It's not depend on the path. So to explain this, I will use a PV diagram, that is pressure volume graph, or it's also known as PV diagram. So let's say I have conditions 1 or state 1 of the gas and state 2 of the gas. So there are 3 ways how the gas will change its state from 1 to 2. These are the pressure and the volume for state 1 of the gas and state 2 of the gas, or system of the thermodynamic. So first, through the path 1, 4, 2, where the initial state will be 1, the final state of the gas is 2. And the second path is 1, 3, 2. And the last path will be from 1 to 2 through the curve. So there are 3 ways how the gas will change its state from initial state 1 to the final state 2. Through path 1, 4, 2, through the curve 1 to 2, and through the path 1, 3, 2. So since the initial state and the final state of the gas are the same, either through path 1, 4, 2, or 1 through the curve to 2, and from 1 to 3, and after that 3 to 2. Therefore, the change in the internal energy of the system or the gas from delta, that which is delta U from 1 to 2 through the curve, 1 delta U 1 to 4 through 2, and the last one delta U from 1 to 3, 3 to 2 are the same, since the initial and the final state of the gas are the same. We still use delta U equal final U minus the initial U, which is the initial U is 1 and the final U will be state 2. So that's the reason why the change in the internal energy of this system, that is the gas system of thermodynamic, independent of path. But this internal energy of the gas is depend on the absolute temperature, which is the temperature in Kelvin, that is related to from the previous topic or chapter, that is 13, kinetic theory of gases. If the initial and the final temperature of the system is the same, for example, the initial temperature, that is state 1, and the final temperature, that is state 2, are the same, or we call also isothermal, means that temperature are same or equal. Therefore, the change in the internal energy of the system will be 0, since the initial T1 is equal to the final T2. Therefore, U2 equal to U1, and then we get delta U 0. And the delta U also 0 for the cyclic process. Means that the initial state and the final state are the same. Let's say the initial state is 1, and then after that the final state also return to 1. Therefore, the delta U is 0. That we call cyclic process. And you must remember the internal energy is not depend on the pressure and volume of the system. So before we go further, so we must know about signs for heat, work, and change in the internal energy of the gas or system. So if you calculate the Q is positive, we call heat flow into the system. If Q negative, heat flow out of the system, where the system is the gas. How about W? If W positive, it will be work done by the system, means that the gas, which is the system, expand. And negative, work done on the system, means that you compress the gas or the system. And if you get the change in the internal energy is positive, it means the internal energy of the gas or internal energy of the system is increased. If negative, vice versa, that is decreased. So actually, when work done by the system, for example, the air molecules is expand, so this molecule of the air loses kinetic energy and does positive work. Means that when the gas expand or the air here is expand, so that the work done is positive because the molecules of the air loses kinetic energy. And how about if compress? What happened to the molecule of the gas, molecule of the air? So the molecule of the air gains kinetic energy. It means that the movement of the air particle or air molecules are faster. Therefore, the kinetic energy will increase, and the air particle does negative work on the piston. So that is about first law of thermodynamics. Now we're going to thermodynamic processes. There are 4 thermodynamic processes. The first one is isothermal, means that temperature the same. Okay. Second is adiabatic, Q is 0, Q equal to 0. The third is isovolumetric, or is also known as isochoric, W equals 0. And the last thermodynamic process is isobaric, delta P or change in pressure equals 0. And after that, we're going also to discuss about PV graph or pressure volume graph for all thermodynamic processes. How we can represent the isothermal, adiabatic, and isovolumetry and isobaric process in the PV graph. These are 4 processes of thermodynamics. The first one is isothermal process. Means that thermal we refer to the heat. Thermal we refer to the heat, and heat related to temperature. So isothermal process, the process at constant temperature. The second one is adiabatic process. During this process, no heat absorbed or released, or no exchange of heat. No exchange of heat. And the third one is isochoric, or it's also known as isovolumetric process. So volume, so the process occur at constant volume. ISO means constant. And the fourth, isobaric process. Bar is the one of the alternative unit for pressure. So in this process, the pressure is constant. So that we will move one by one, from process 1 to 2 and 3, and after that the 4. Isothermal process, where the temperature are the same, temperature 1 equal to temperature 2, or initial temperature of the process equal to the final temperature of the process. So actually this is thermodynamic process that occur at constant temperature. If the temperature are constant, therefore the change in the internal energy of the system, which is undergoes isothermal, is equal to 0. So that the first law of thermodynamics, that is Q equal to delta U plus W, can be written as Q equal to W. It means if the heat Q flow out from the system, so the Q is negative. Therefore, W also negative. So if the heat flow, or you supply the heat to the system, that Q flow into the system, so the Q will be positive. Therefore, W also positive, means that the gas will expand. Alright, so what is the isothermal changes? So since the process occur at constant temperature, so we have a gas law related to this, which is Boyle's law. So we can apply Boyle's law equation to solve isothermal changes. So the isothermal changes is either the gas expand or the gas being compressed isothermally. For both expansion and also compression, the temperature remain unchanged and related to the Boyle's law. So we can apply these two equations to solve a problem in isothermal changes, either expansion or compression. So when the gas expands isothermally, so the final volume will be greater than the initial volume. So means that the gas expand, so the gas do positive work. And then the Q will be positive because Q equal to W for the Q equal to W for isothermal changes, since delta U equal to 0. For compression, the final volume will be smaller than initial volume, so compress. So the gas did a negative work done, so that the Q also negative. It means if W negative, Q also negative. If Q negative, W also negative, and vice versa. So the second law, the second process will be adiabatic process. Process is an adiabatic process is one of the thermodynamic process that occur without heat transfer into or out of the system. So means that Q equals 0. There is no exchange of heat, or I can write down Q equals 0. So that the first law of thermodynamics become delta U equal to negative W. Delta U equal negative W. So we know delta U is final internal energy minus the initial internal energy. For example, in the compression stroke in the internal combustion engine, is approximately adiabatic process. Actually, adiabatic process is the compression and expansion of the gas occur quickly. For example, you compress the gas quickly or the gas expand quickly. So that is adiabatic process, where there is no heat transfer into or out of the system. So the Q equals 0. For the first law, it becomes delta U equal to negative W for adiabatic process. For example, when during the adiabatic expansion, so where the final volume greater than initial volume, so the work done will be positive. Because expand, W will be positive. So delta U will be negative because delta U equal to negative W for the adiabatic changes. So if expand, W positive. So positive times negative, you get delta U negative. It means U decrease. Or final internal energy smaller than the initial internal energy. That's the reason why delta U will be negative. So meanwhile, for the adiabatic compression, where the final volume smaller than initial volume, so the delta U will be positive because W negative. So I can show U, delta U equal to negative W since compression. So W is negative. So negative multiplied with negative, we get positive. We get positive. So means that the change in the internal energy, which is delta U positive, means that U increase, or the final internal energy, that is U2, greater than U1. So as the conclusion for this adiabatic changes, whether it's expansion or compression, so the work done will increase. The work done will change the temperature of the body. For example, like in the case of expansion, the U is decreased, therefore the temperature also decrease. Temperature of the body or the system will decrease. And for the adiabatic compression, since the internal energy is increased, hence the temperature of the system or the gas will increase. Since we know the formula of internal energy of the gas, degree of freedom over 2 and RT. Alright, so now we go to the third process, which is isochoric or isovolumetric. It's a process that occurs at constant volume. So when constant volume, there is no expansion and compression of the system. Therefore, work done equal to 0 because there is no change in volume. Therefore, work done for this process equal to 0. So the Q equal to delta U plus W, that is the first law equation, can be written as Q equal to delta U. Q equal to delta U, where the delta U is final internal energy minus the initial internal energy. So during this isochoric process, when you supply the heat to the system, the Q is positive. Q positive. You supply Q positive, thus delta U also positive. Means that the U is increased. Then temperature also increase. So if the heat flow out from the system, the Q will be negative. Thus delta U negative means the internal energy of the gas or the system is decreased. Therefore, the temperature of the gas or the system will decrease. So means that the Q here is a factor that will increase the internal energy of the system. Increase or decrease the internal energy of the system. It depends on the Q. If the Q is positive, so the delta U also will positive, and then the internal energy, the temperature will increase. So, and another way around, or vice versa. For example, heating a gas in a closed constant volume container is an isochoric process. So when isochoric or isovolumetric process is related to a gas law which is at constant volume, which is pressure law or Gay-Lussac's law. And the last process will be isobaric. It's a process that occurs at constant pressure. Related to the constant pressure gas law, which is Charles' law. Charles' law, where V is directly proportional to the temperature at constant pressure, is referred to the Charles' law. So you may apply the equation of Charles' law to this isobaric. So when constant pressure, the change in pressure equal to 0 and the work done equal to P delta V, so that the first law of thermodynamics can be written as Q equal to delta U plus P delta V, where the P is pressure and delta V is change in volume. So now we are going to look at on the graph pressure against volume for the thermodynamic pressure processes. Where here I will draw 4 Boyle's law curve. The higher is T4, the lowest is T1. It means that T1 lower than T2 temperature and lower than T3 and lower than T4, where the highest temperature will be T4, shown by this relation. So we have state A. So consider the initial state of the gas or system is A, and after that, where the pressure and the volume is P1 and V1, and after that this system expand to state B on the curve level T2. So on the curve T2, the temperature A and the B are the same. So this is the process of isothermal. Isothermal. And then the second process, from A, the initial state of the system is A, and the final to C. So this system expand from A to C, and this process is adiabatic process because the temperature is dropped from A, from temperature T2 to temperature T1, where the final is state C for the adiabatic process. This we call the adiabatic expansion because the volume C greater than volume A. And then if you can see, there are 2 curves here. One is isothermal and the second one is adiabatic. We can differentiate these 2 curves by observing, by analyze the gradient. The adiabatic curve, that is A to C gradient, always greater than the gradient of the isothermal curve, that is AB. So that is how we identify which one is adiabatic curve, which one is isothermal curve, by compare the gradient. So in this case, the temperature of the state A will change, will drop from A to C, where the temperature T1, that is Tc, is smaller than the temperature Ta, that is T2. But if isothermal, the temperature unchanged or constant. Okay, the next process from state A to state D. So this is isovolumetric or isochoric, because the volume are not changed from A to D. The initial state is A, the final state is D. Only the pressure will drop from P1 to P2. And the last one is from A to E. State A to E, this we call isobaric process. Because you can see along the process A to E, there is no change in pressure. And this is expansion. Expansion, isobaric expansion. So that about the graph of PV, the graph of PV, or we also call as pressure volume diagram or PV diagram, to represent for thermodynamic processes. So now we go to the last subtopic. It's about thermodynamic work. So the outcome is discuss work done in isothermal, isovolumetric and isobaric processes only. So the adiabatic work not going to be discussed in this level. You will learn this in higher level, not in matriculation level. So first, how to calculate work done in system. So we will apply this equation. That is the W equal to integrate P dV from V1 to V2, where the V1 is initial and the V2 is final. And also same as area under the PV graph. And that will be work done. So you must remember this very important key. So if they give you the graph pressure against volume of PV diagram, so you need to calculate the area under the graph in order to calculate the work done. And show by these four graphs. The first graph, initial state at the left of final state, that 2. So it means that the gas expand. When the gas expand, the gas do positive work. So the work done will be positive. That is greater than 0. The second graph, another way around, where the initial at the right and the final at the left. So this is compression of the system. We compress the gas or the system. So the work done will be negative. That is smaller than 0. So this arrow that show the change of gas or system from state 1, the initial, to the final state is very important. For example, like graph A, expansion. Graph B, compression. So we refer to the direction of the arrow here, where there is expansion or compression. And then the third, or C, so this one is isobaric expansion. So the work done is also positive, but we can calculate the area under the graph, which is the area of this square. So the, or rectangular. So the length time width. So you get P1 bracket multiply with V2 minus V1. So it should be greater than 0 because this is expansion. And the D. So this is the isovolumetric or isochoric. So there is no area under this line, so it will be 0. So the work done will be 0. So this, the A is isothermal expansion, B isothermal compression, for C is isobaric, and D isochoric or volumetric. And after this, I will show the the equation to calculate the work done for isothermal, isobaric, and also isochoric. We go to the work done in isothermal process. So the formula to calculate the work done, either expansion or compression, isothermal, during the isothermal process, we apply formula W equal to nRT ln V2 divided by V1, where the N is number of mole, the W is work done, the R is molar gas constant, the T is temperature in Kelvin, V2 is final volume, and V1 initial volume of the system or the gas. Or we also can use another formula of work done during the isothermal process, that is nRT ln pressure 1 divided by pressure 2, where the pressure 1 is initial pressure and pressure 2 is final pressure. And since the delta U is equal to 0, so the Q here is also equal to W. Therefore, Q can be calculated by using the formula of work done. that for the isothermal process. So now we go to the isobaric process. So in isobaric process, the pressure is constant, so we may apply the formula W equal to P multiplied with change in volume, or we can expand the delta V as pressure multiplied with V2 minus V1. And the last process will be isovolumetric or isochoric process. There is no volume because the gas or the system not been expanded and also not been compressed. Therefore, the change in volume equal to 0. So after we apply W equal to integrate P dV, since dV is 0, so that the work done is also equal to 0. So these are the formula to calculate the work done for isothermal, isobaric, and work done for isovolumetric process. So the example how to solve the problem regarding to the thermodynamic processes, you're going to discuss in tutorial session. With that, I end this topic about C1 and C2 level, and good luck for your first examination. Thank you very much, and good luck again.